apply to convergence in rational difference equations.
Okay, so I am one of the current students of Dr. Zeilberger, and so this research is going to be applied towards my PhD. So what we're trying to do is apply some experimental techniques to finding convergence of these rational difference equations, and this is work that has been inspired and motivated by Dr. Zeilberger, so thank you. Right. So the goal in these kinds of problems is to describe the limiting behavior of a rational difference equation, of the sequence described by a rational difference equation. And we have the n plus first term is written as a function of the k plus 1 previous values. And we're going to make sure that we don't divide by 0 ever. So the arbitrary initial conditions are going to have to be positive, and any coefficients that we have in this rational function are going to be positive. Now, most of the work that's currently done has numerator and denominator being linear functions, so it's not necessary, but that's just what the model is right now. Right, so here's an example where the n plus first term is a very easy recurrence in terms of the previous value, and the 9/20th is just so the arithmetic works out for the example throughout the talk. All right, so when I said limiting behavior, I really just want to know about convergence. And if it does converge, it's going to be to an equilibrium point, which is a solution to this equation here. And of course, since everything that we started with is positive and our coefficients are positive, we need the positive equilibrium. So in our example, we have two solutions, 4/5 and minus 5/4. So 4/5 is the one that we want. And there are two general types of convergence that people look at. The first is local convergence. That is, if we start with initial conditions that are close to this equilibrium point, does that guarantee convergence? But what I'm interested in is global stability, and that is if we start with any positive initial conditions, do we converge? And so Dr. Zeilberger gave me some tips and a method that I should try, and I've been implementing that. I'm going to give you a 3-step method in which the first 2 steps are kind of just to make the notation work out nicely, and the third step is where the big idea comes in. All right, so first, well, I would prefer that the equilibrium be at 0, so that we always have the same value that we're converging to. So I'm just going to move the equilibrium to 0 by subtracting the x bar from each term in the sequence. And we can find then a new rational difference equation for this new sequence very easily. And here's the example. You know, we substitute in this xn minus x bar equals the n, solve, and get a new function. And now we require the initial conditions to be greater than minus x bar rather than greater than 0. And we're going to call such initial conditions admissible so that we can look through it later. And we've also lost the positivity of the coefficients, but that's not a problem because if we didn't divide by 0 in the original case, we're not going to divide by 0 now. All right, so the next thing is when we really like a function, well, our 0 function was from a vector of length k plus 1 to scalar, and so that's not something we can iterate easily. We can't compose it with itself. So I just need a function that we can compose with itself, and that's this q function. It's really, you can think of it as just a moving window. You line up the sequence on a piece of paper. The first value is the first initial conditions, and then you just kind of inch along on this sequence. Okay, so just going to denote capital Zn by the vector that ends at the nth term of the sequence. And now we have Zn is going to be this q composed with itself n times on the initial condition. And this allows us to describe this global asymptotic stability as an easy limit of a function composed with itself n times, and we want this to go to 0 because we can move our equilibrium point to 0. Okay. Now, here's where the real idea comes in, and that is basically we want to show that this sequence is kind of bounded by a geometric sequence that converges. So I claim that if we can find a positive integer k and the delta between 0 and 1, such that this expression here holds, that is, if we take the Euclidean norm of the q function iterated k times on any admissible vector, and we divide that by the Euclidean norm of that admissible vector, if that's less than this delta, which is less than 1, then we have this global asymptotic stability. The limit goes to 0, as long as we started out, of course, with an admissible initial condition. All right, so you probably all see why this is true, but let me just explain it here. So let's consider the first k iterations of q. That is, we have the initial conditions and then all the way up to iterating q k times. And we're going to let this capital Z without the subscript be the maximum of the norms of all of these initial k iterates. All right, so if the conditions of this claim are satisfied, that I have up here still, then you probably agree that this is true. If we iterate this q to the k n times on any one of these, this is less than delta to the n times the norm of this one, which of course is less than this. And each zi is really just q to the I of z0. So we can have q to the nk plus I z0 norm. And since delta is less than 1, the right-hand side goes to 0, and we have the convergence that we want. All right, so let's continue our running example and show how that this has global asymptotic stability. Right, so we've already transformed the equilibrium point to 0 here. We want to keep track of this fact that x bar originally was 4/5. And I claim that k equals 2 will work. And that's very easy. If I just show you that this maximum here is less than 1, then that's it. All right. Well, q squared, remind me what this is our original function. We just have to iterate that one more time, and we get this guy. And do some, arithmetic, take some norms, do some cancellation, and